Okay, in this video I'm going to continue with a discussion of Boolean functions, and we're going to consider the case of n equals 2. And let me remind you, a Boolean function is a function f which maps a string of n bits in a row to a single bit. So the domain is sequences of zeros and ones of length n, and the range is either a 0 or a 1. Okay, so I'm going to take the case n equals 2, and we found out that the number of possible Boolean functions that is, the number possible that we could define is equal, we call it capital N, and it was 2 raised to the 2 to the n power. And that's 2 to the 2 to the 2, which is 2 to the 4th, which is 16. So there's 16 possible Boolean functions that I could define for the case n equals 2. And what I'm going to do then is I'm going to say that my domain, just to remind you, is the set of 4 elements 0, 0, 0, 1, 1, 0, and 1, 1. And what we're going to do is we're going to call those P and Q. So we could say that the domain, we could use the full notation and write them out as ordered pairs rather than the shorthand. And using some set theory notation, just for practice here, I could write this set out in set builder notation as the ordered pairs P, Q, such that P is an element of the set 0, 1, and Q is an element of the set 0, 1 also. Okay, so that's the domain. And basically what I'm going to do is I'm going to use a tabular representation to define that domain, a function, and I'm going to use P and Q as the names of the 2 bits in the sequence. So I'm going to define the function here, and I have 4 possible inputs. My domain has 4 possible, and instead of just writing 0, 0, 0, 1, 1, 0, and 1, 1, I'm actually going to call the first one P and the second one Q, and label them like this. Okay? And now, again, using that counting principle, I had 2 choices for the function with input 0, 0, 2 choices with the input 0, 1, 2 choices with the input 1, 0, and 2 choices with the input 1, 1. And that's where I get my 2 to the 4th. 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 are the number of ways that I can define this function. Okay, I'm going to define some special ones though. So for example, I could say that f of P and Q is equal to 0. No matter what P and Q are, the output is 0. And I could fill that in like this. All zeros. No matter what P and Q are, I get 0. I could define another function, let's call it g of P and Q, such that the output is P itself. And I could go ahead and define g over here, and the output is supposed to be P, and P is a 0 here, so it doesn't depend on Q at all. P is a 0 here. On the 3rd line, P is a 1, and on the 4th line, P is also a 1. So this is another possible function. Another possible function is Q itself. Okay, so the function h now only depends on Q, and the pattern for Q is a 0, 1, 0, 1. So I'm just going to repeat that pattern here to define the function h. Okay, so if we use the P and Q notation here, we can define a number of different functions. So what I'm going to do is I'm going to go ahead and show you some special functions. Okay. So I have two different constant functions. Let me label this for n equals 2. Special Boolean functions. We have two constant functions. We have f of p and q equal to 0, and we have f of p and q equal to 1. Okay, those are two possibilities. Okay. Now, the two f's are different here because I've defined them differently, but instead of using f, g, and h, I'm just going to use f all the time on this paper, or on this page, okay? These two functions are different. They're defined differently. But so technically I should use a g for this one, but I'd run out of letters because I'm going to define a whole bunch of them on this page, okay? I could define what's called the AND function, where f of p and q is equal to, and here's another way of using curly brackets, I'm going to say it's equal to 1 if both p and q are equal to 1 and q equals 1, and 0 otherwise. Okay? And what we're going to do is we're going to interpret p and q as true and false values. Let me make the table with the 4 values in it. And I'm going to interpret a 0 as being a false and a 1 as being true. And we have, and in the English language, the definition of the AND. If I say, you know, both P and Q are true, that means that the AND function is going to be false unless both P and Q are true. And here is the only case where both P and Q are true, so this is the only case where I have a 1. Okay? I can define the OR function. F of P and Q is equal to a 1 if either P equals 1 or Q equals 1. And you can see I'm defining the AND function in terms of the English language and I'm defining the OR function in terms of the English language OR. 0 otherwise. And you know what I'm going to do? I'm going to say either P equals 1 or Q equals 1 or both P and Q equal 1. How do I erase this here? Okay. P equals 1 and Q equals 1. And in this one, I'm going to have the OR function. And so either one of them being true gives me a true. And if they're both true, I also get a true. Okay? I can define the XOR, where it's either or, but not both. P equals 1 or Q equals 1, but not both. Okay? And I denote the XOR. I'll show you the symbols for all of these. And this is going to be a 0, 1, 1, 0 in the pattern because it excludes the possibility of them both being true. That gives me a false. But not both. Either P or Q being true gives me a true function on the XOR, but it doesn't allow both of them to be true. And so these are some of the most basic Boolean functions that we'll deal with. And you're going to see now that what we're going to do is we're going to start doing our logical analysis using Boolean functions. And I'll stop there.